And, well, we give you the shortcut to being really well informed. Today, we're diving into something incredibly small, but profoundly important. We're talking about the meson.
A fascinating particle indeed.
Absolutely. Its story is just amazing. It starts out as this idea, this sort of nuclear glue, right? The thing needed to explain why atomic nuclei don't just pop apart.
That was the initial puzzle, yes.
But it goes so much further. Our mission today, for you, is to figure out why these particles, often incredibly short-lived, hold clues to the universe's biggest secrets. We're talking fundamental forces, why matter exists at all, instead of just antimatter. It's genuinely mind-bending stuff.
And mesons are right in the thick of it. It's crucial to understand they aren't fundamental themselves, like an electron or a quark. They're composites, made of smaller pieces.
Yeah.
But they hold this really pivotal position in what we call the standard model of particle physics. They're key players.
Okay, composite, not fundamental. Got it. So let's zoom in. The subatomic world. It sounds chaotic. How do physicists even start sorting things out down there? And where do mesons actually fit in? What is a meson, fundamentally?
Well, at a high level, we have two main families, leptons and hadrons. Leptons, like electrons, neutrinos. They're fundamental and they don't feel the strong nuclear force.
Okay, leptons ignore the strong force.
Right. Hadrons, on the other hand, do feel the strong force. But, and this is key, hadrons aren't fundamental. They're made of quarks.
Ah, quarks. Okay, so hadrons feel a strong force because they're made of quarks, and hadrons themselves split into types.
Exactly. Two main types of hadrons, baryons and mesons. Baryons are things like protons and neutrons and the stuff making up atomic nuclei. They're built from three quarks.
3 quarks are baryons, okay.
But mesons are different. They consist of one quark and one antiquark. Just QQ-bar, as we sometimes write it.
1 quark, 1 antiquark. Seems simple enough, but you said this difference has big consequences.
Profound consequences. It starts with spin. Quarks are fermions. They have this quantum property called spin, which is half integer, like 12.
Okay, spin 12 for quarks.
Now, if you combine 3 spin 12 quarks, like in a baryon, the total spin is also half integer, so baryons are for fermions. But if you combine a spin 12 quark and a spin 12 antiquark, their spins can add up differently. They can combine to give an integer spin like 0 or 1.
Ah, integer spin, not half integer.
Precisely. And particles with integer spin are called bosons. So mesons are bosons.
Okay, so baryons are fermions, mesons are bosons. Why is that distinction so critical?
It's fundamental. Fermions are, the building blocks of matter. They obey strict rules about not sharing the same quantum state, think electrons in an atom. Bosons, however, often act as force carriers. They can share the same state. This bosonic nature is why mesons could be conceived as force carriers, like Yukawa originally proposed. It also relates to other properties, like baryon number. Quarks have baryon number plus 13, and a quark's Nesor 13.
So 3 quarks give a baryon number of plus 1. Makes sense for protons and neutrons.
Exactly. But a quark and an antiquark pair, their baryon numbers cancel out. B equals 0 for mesons.
B equals 0, and that affects how they decay.
Yes. It means they can decay into particles like photons or lepton pairs without violating baryon number conservation. Protons, having B1, are stable. For this reason, there's nothing lighter with B1 to decay into. All mesons, however, are unstable.
Universally unstable. Okay. And what about this color charge you hear about with quarks? How do mesons handle that? They have to be neutral somehow, right?
That's right. Quarks have a property we call color charge, red, green, or blue. Antiquarks have anti-red, anti-green, or anti-blue. It's just an analogy, of course, not actual color. The theory of the strong force, quantum chromodynamics, or QCD, states that only color-neutral or white combinations can exist freely.
Like mixing colors of light to get white.
Kind of. For a meson, you achieve this by combining a color with its anticolor. A red quark with an anti-red antiquark, for instance. The combination is color-neutral.
Okay, that makes sense. And they're composite, so they have a size. And you mentioned unstable. How unstable are we talking?
They do have a physical size, yes, around a femtometer, maybe 60% of a proton's diameter. And universally unstable is correct. All known mesons decay. Their lifetimes vary wildly, though. Some decay almost instantly via quark-antiquark annihilation, maybe 10-23 seconds. Others, where a quark has a changed flavor via the weak force, can live much longer, relatively speaking, maybe up to 10 seconds.
Wow, huge range. So definitely not hanging around in everyday matter. You make them in accelerators or find them from cosmic rays.
Exactly. They're transient players produced in high-energy interactions.
Okay, now this is where the history gets really juicy, I think. Let's go back to the 1930s. Big problem. The nucleus. Protons are positive. They should repel, right? Violently. What holds them together?
A major puzzle. Clearly, there had to be another force, something incredibly strong but only acting over very short distances confined to the nucleus.
The nuclear glue.
Precisely. And in 1935, Hideki Yukawa had this brilliant insight. He thought about the electromagnetic force being carried by photons.
Okay, photons carry EM.
So Yukawa proposed maybe the strong nuclear force is also carried by a particle. A new quantum particle exchanged between protons and neutrons. He calculated its properties. Because the force was short range, unlike electromagnetism, the carrier particle had to have mass. His calculations put its mass somewhere between the electron and the proton.
Hence meson for middleweight.
Exactly. It was a radical idea, a massive force carrier. People were used to the massless photon.
And he actually predicted the mass needed.
He did, using the uncertainty principle. He linked the force's range, about 10-15 meters, to the particle's mass. The relation is roughly R is proportional to h bar over mc.
Okay, standard quantum stuff.
Right, and that gave a mass around 200 times the electron's mass. His theory also described how charged versions, pions, could mediate the transformation between protons and neutrons, effectively binding them.
Incredible. And then, just a couple years later, Anderson and Nettermeyer, looking at cosmic rays, they found something.
They did. A particle with a mass around 106 MeV, which was, remarkably close to Yukawa's prediction.
So everyone thought, Eureka! Found it! They called it the mu-meson, right? No, just the muon.
Yeah, it was the initial reaction, yes. It seemed like the perfect fit. The nuclear glue had been found.
But there's always a but in physics, it seems. This particle, the muon, it didn't really act like glue, did it?
That was the paradox. Later experiments, crucial work by conversely, Pancini and Piccini in Italy, showed the muon barely interacted with nuclei at all. It sailed right through matter, behaving like a heavy electron, not a mediator of the strong force.
So, right mass, wrong personality. That must have been confusing.
Deeply confusing. The solution came from theorists like Sakata and Inouye in Japan, and Marshak and the Bethe in the U.S. They proposed the two-meson hypothesis.
Oh, okay. Two particles involved.
Yes. They suggested that Yukawa's actual particle, the strongly interacting one, was being produced high up in the atmosphere by cosmic rays. But this true meson was unstable and quickly decayed into the weakly interacting particle, the muon, which is what Anderson and Nettermeyer were detecting down at sea level.
Ah, so the muon was the decay product, not the original glue particle. Clever.
Elegant hypothesis. And it set the stage for finding the real meson.
Which brings us to 1947. Cecil Powell and his team at Bristol, they had this amazing technique, right? Photographic emulsions.
Yes, a brilliant experimental technique. They used special photographic plates that could record the tracks of charged particles. Powell's group, including Lattes, Occhialini, Kurz, Roberts, exposed these emulsions at high altitudes on mountains like the Big Demeti.
Closer to where the action happens with cosmic rays.
Exactly, and they found it, the smoking gun.
What did they see?
They saw tracks in the emulsion showing one particle coming to rest and then another particle track emerging from the stopping point. A clear decay event.
Wow. A picture of it happening must have been incredible.
Truly a eureka moment. They identified the first particle, the primary one, as having a mass consistent with Yukawa's prediction and showing signs of strong interaction. They named it the pion, or pi-meson.
The pion, finally.
And the secondary particle, the decay product, it was the muon. They saw the decay. Pion decaying into a muon plus something neutral, which we now know is a neutrino.
So that confirmed Yukawa, resolved the muon confusion, landmark stuff.
Absolutely, a watershed moment.
Yeah.
Yukawa got the Nobel in 49, Powell in 50. It really highlights how science works sometimes through confusion and misidentification towards the right answer.
So the pion opened the floodgates. But then things got messy again, right? The 1950s and 60s, accelerators start producing tons of new particles. The particle zoo.
Indeed. A bewildering variety of short-lived particles emerged from experiments. It became clear they couldn't all be fundamental. We needed a deeper level of organization.
Like the periodic table for elements, but for particles.
Something like that. The breakthrough came in 1964. The quark model, proposed independently by Murray Gell-Mann and George Zweig. They suggested that hadrons, baryons, and mesons alike were built from more fundamental things. Quarks. Mesons specifically were a quark paired with an antiquark, Q bar.
So the zoo animals were actually made of just a few types of quarks.
Precisely. This built on earlier work, like Gell-Mann's eightfold way, which had already started grouping hadrons into patterns based on properties like strangeness and isospin. The quark model provided the underlying physical reason for those patterns.
Okay, so quarks brought order. How do we use them to classify mesons today? You mentioned flavors. Up-down strange.
Yes, there are 6 known flavors of quarks, grouped into 3 generations. Up and down, generation 1, charm and strange, generation 2, and top and bottom, generation 3. The top quark is too heavy and decays too fast to form mesons, though.
6 flavors, minus the top for meson building, and the families are named after the quarks.
Generally, after the heaviest quark involved, so you have light unflavored mesons, made only of up-down strange quarks and antiquarks, net strangeness 0. Pions are the prime example, up-down quarks. They still mediate the long-range part of the residual nuclear force.
The original nuclear glue is still relevant. Okay.
Strange mesons contain one strange quark or antiquark, like the kaons, K-mesons. Their discovery introduced strangeness, and their decays revealed fundamental symmetry violations.
Parity violation, CP violation, big stuff came from kaons.
Huge. Then, charmed mesons, containing a charm quark or antiquark. D-mesons are examples. The big moment here was the November Revolution in 1974.
The JED discovery.
Exactly. Discovered simultaneously by Richter at SLAC and Ting at Brookhaven. It was identified as a hidden charm state, a charm quark and its antiquark bound together, CC bar. This was undeniable proof of the charm quark.
A revolution indeed. And bottom.
Bottom mesons, containing a bottom quark or antiquark, B-mesons. The epsilon particle, discovered in 1977, was the hidden bottom state, bar, confirming the 5th quark.
And B-mesons are super important now, right, for looking beyond the standard model.
Absolutely critical. They're our main laboratory for studying CP violation in detail and searching for subtle signs of new physics, largely because the bottom quark is heavy and decays in many ways.
So flavor is one way to classify. But you also mentioned JPC, this quantum fingerprint. Sounds more technical.
It is, but it's crucial. J is the total angular momentum, spin. P is parity, how it looks in a mirror reflection. C is charge conjugation, swapping particles for antiparticles.
JPC, okay.
The simple quark-antiquark model predicts only certain combinations of J, P, and C are possible. For instance, combinations like 0 plus mech or 1 plus shouldn't exist for a simple Q-bar state.
So if you find a particle with one of those forbidden JPCs...
It's smoking gun. It signals something more complex is going on, maybe a hybrid meson with an excited gluon, or even a glue ball made only of gluons. The hunt for these exotic JPC states is a major focus.
Hunting for rule breakers. Cool. And even for normal mesons, JPC helps sort them.
Definitely. The most common ground state mesons, with 0 orbital angular momentum between the quarks, fall into 2 main groups based on spin alignment. Pseudoscalars, JPC equals 0 plus. Quark spins are anti-aligned, total spin S0. Pions, kaons, eta meson, for examples.
Okay, spins opposite.
Vectors, JPC 1. Quark spins are aligned, total spin S1. Rho, omega, phi mesons are examples.
Spins parallel, and you mentioned a big mass difference between these.
Yes, a very striking difference, even for the same quark content. The Rho meson UD bar spins aligned is about 770 MeV-C, while the pion UD bar spins anti-aligned. It's only about 140 MeV-C1.
Wow, more than 5 times heavier just by flipping a spin.
It's called hyperfine splitting. It comes from the spin-spin interaction between the quark and antiquark, mediated by gluons. It's a key prediction of QCD.
Okay, that brings us back to the strong force itself. You said Yukawa's idea is now an effective theory for the residual force. Can you unpack that a bit more? How is the force between nucleons different from the force inside them?
Great question. Think of it like electromagnetism in chemistry. Inside an atom, you have strong electric forces between the nucleus and electrons. But the atom as a whole is electrically neutral.
Right.
Yet 2 neutral atoms can attract each other weakly through van der Waals forces, which arise from temporary fluctuations in their electron clouds. It's a sort of leakage of the internal electric forces.
Okay, I get the analogy, so the nuclear force is like that.
Exactly. Protons and neutrons are color neutral overall, like neutral atoms. But the incredibly strong color forces binding the quarks and gluons inside them aren't perfectly contained. A small fraction leaks out. This leakage creates a force field felt by nearby nucleons. That's the residual strong force, the nuclear force. And in this picture, it's mediated by the exchange of virtual mesons, mostly pions for the longer range part, heavier mesons for shorter range details.
So the force between nucleons is just a shadow, a residue of the much stronger force within them.
Precisely. That's why it's shorter range and, relatively speaking, weaker than the fundamental color force described by QCD.
So QCD is the fundamental theory. And mesons aren't fundamental particles in QCD, they're emergent, bound states.
Exactly. They emerge from the interactions of quarks and gluons. Studying them is therefore a critical way to test QCD.
What key QCD ideas do mesons help us test?
Well, first, color confinement. The fact that we only see color-neutral mesons and baryons, never free quarks. If you try to pull the quark and antiquark in a meson apart, the energy in the gluon field between them grows. Eventually, it's energetically cheaper to create a new quark-antiquark pair from the vacuum. The flux tube snaps, and you get two mesons instead of free quarks. Confinement holds.
Can't pull them apart, the string just breaks and makes more mesons. Got it. What else?
There's asymptotic freedom, the idea that the strong force gets weaker at very short distances or high energies. This allows certain calculations in QCD.
Okay, weaker up close. Counterintuitive.
It is. But perhaps the most profound connection is chiral symmetry breaking. This is a bit abstract, but crucial. Imagine a world where the lightest quarks, up and down, had zero mass. QCD's equations would have an extra symmetry called chiral symmetry.
A hypothetical perfect symmetry.
Yes. But the actual ground state of QCD, the vacuum, doesn't respect this symmetry. It's spontaneously broken.
The vacuum itself breaks the symmetry.
Correct. And there's a theorem, Goldstone's theorem, that says when a continuous global symmetry is spontaneously broken, massless spin-zero particles, Goldstone bosons, must appear.
Massless particles pop out of the broken symmetry.
And for QCD, the pions and cans, eta, are identified as almost Goldstone bosons. They're not quite massless because the quarks do have small masses, so we call them pseudo-Goldstone bosons.
Whoa. So the pion being so light isn't an accident. It's because it's tied to this deep symmetry breaking in the vacuum.
That's the profound insight. Its lightness is a direct consequence of the structure of the QCD vacuum. Vector mesons, like the rho, aren't protected by this symmetry, hence they're much heavier.
That's amazing. Studying meson masses tells us about the vacuum itself. How do theorists check this?
Through sophisticated tools like Lattice QCD, which performs massive numerical simulations on supercomputers, and analytical frameworks like QCD sum rules, the agreement between these theoretical predictions and experimental measurements of meson properties is a major triumph for QCD.
Okay, so to do those experiments, we need mesons. How do we actually make them? You mentioned cosmic rays and accelerators, EMC Garot.
That's the fundamental principle. Convert energy into mass. Naturally, high-energy cosmic rays hitting the atmosphere do this constantly. That's how pions were first found.
But for controlled studies, accelerators.
Yes, two main types. Hadron colliders, like the LHC, smash protons together, or protons and antiprotons. Really, it's the quarks and gluons inside colliding. Processes like two gluons fusing or a quark and antiquark annihilating can create new quark-antiquark pairs.
Which then have to grab partners and become mesons due to confinement.
Exactly. They hadronize into jets of particles, including many different mesons. It's a bit messy, but produces huge numbers.
And the other type?
Electron-positron colliders, like SuperKKB powering the Belle-6 experiment. Here, you collide an electron and its antiparticle, a positron. They annihilate completely into pure energy, a virtual photon, or Z boson.
Cleaner starting point?
Much cleaner. This energy state then converts back into a quark-antiquark pair, which hadronizes into mesons. You don't have the leftover bits of protons flying around.
And you can tune these colliders, like the B factories.
Precisely. B factories like SuperKKB are tuned to an energy that specifically produces a particle called the upsilon 4s. This particle decays almost 100% of the time into a pair of B mesons, one B and one anti-B.
So it's a B meson factory line, incredibly efficient and clean source.
Exactly. Perfect for studying B meson properties in detail.
Okay, so we make them, and then almost immediately they decay. You called their decay a force-emitter. Can you expand on that? How does the decay tell us which force is at work?
It's all about the lifetime and the decay products. The stronger the force mediating the decay, the faster it happens, the shorter the lifetime. Strong decays. If a meson is heavy enough to decay into lighter hadrons without changing quark flavor, like a rho going to two pions, the strong force handles it. Lifetimes are incredibly short, 1024 to 1022 seconds. Blink and you miss it, many times over.
The fastest route.
Electromagnetic decays. If a strong decay is forbidden, maybe by conservation laws like parity, but the meson can decay via photons, the electromagnetic force takes over.
Yeah.
It's weaker, so lifetimes are longer. 1021 to 1016 seconds.
Okay, noticeably longer. Example.
The neutral pion. That's the lightest hadron, so it can't decay strongly. It decays electromagnetically into two photons. Its lifetime is around 8 by 10, 17 seconds, millions of times longer than the rho. This decay was actually key evidence for quarks having color.
Interesting. And the slowest decays?
Weak decays. If neither strong nor EM decays are possible, the meson must decay via the weak force. This is the only force that can change quark flavor, like strange to up, or charm to strange, or bottom to charm.
A flavor-changing force.
Yes. Since it's the weakest, the lifetimes are the longest comparatively. 1013 up to 10 to 8 seconds for particles like kaons.
So kaons, D-mesons, B-mesons containing strain, charm, bottom quarks, they mostly decay weakly.
Primarily, yes. The K plus meson US bar decays because the strange antiquark weakly transforms into an up antiquark. D-mesons decay when the charm quark changes. Me-mesons decay when the bottom quark changes. The whole field we call flavor physics is essentially studying these weak interactions using heavy mesons as our natural laboratories.
Incredible. So this ability to track forces and flavors makes mesons vital tools for tackling the big unknowns, right? Like finding new kinds of matter or understanding the matter-antimatter imbalance.
Absolutely. Those are the frontiers where mesons are playing a leading role. Take the search for exotic mesons.
Things beyond the simple quark-antiquark picture.
Exactly. QCD allows for more complex color-neutral combinations we're actively hunting for. Glue balls. Particles made only of gluons. Pure force. Theory predicts them. The X23SD particle seen by the BSIS experiment in China looks like a very strong candidate for the lightest pseudoscalar glue ball. Its properties match theoretical predictions remarkably well.
A particle of pure glue. Wow. What else?
Tetraquarks. 4 quarks bound together. 2 quarks, 2 antiquarks. These could be compact objects or looser molecules of two mesons. LHCb at CERN has found many candidates like the Z4430 plus or the doubly charmed KCC plus here. Their quark content must be more than just Q-bar, hybrid mesons. A quark-antiquark pair with an extra excited gluon contributing significantly to its properties.
How do you even spot these amidst all the normal mesons?
It's tough. You look for extra states that don't fit the established Q-bar patterns, or particles with those exotic GPC values we talked about, or ones that decay in very unusual ways. It's like finding unexpected species in the particle zoo. Many candidates are still tentative.
Fascinating. And connecting this to the cosmos, the matter-antimatter mystery, mesons help there too.
Immensely. The Big Bang should have made equal matter and antimatter. We're here because matter won out. This requires a difference in how matter and antimatter behave, known as CP violation.
Which was first seen in kaons, right?
Yes, back in 1964. The standard model includes CP violation via the CKM matrix, which describes how quarks change flavor in weak interactions. But the B-meson system is where we can really put it under the microscope. The effects are larger and easier to measure. Experiments like Babar, Bell, LHCb, and now Bell II have made incredibly precise measurements of CP violation in B decays.
And do the measurements match the standard model's prediction from the CKM matrix?
So far, remarkably well. All the different measurements seem consistent with the standard model CKM mechanism.
Okay, but didn't you say there's still a puzzle?
Yes, and it's a huge one. The amount of CP violation predicted by the standard model CKM mechanism is far too small by many orders of magnitude to explain why the universe is dominated by matter.
Ah, so the standard model has some CP violation, but not nearly enough.
Exactly. This is one of the most compelling pieces of evidence that there must be new sources of CP violation and therefore new physics beyond the standard model. Studying B-mesons and K-mesons and D-mesons with ever higher precision is one of our best hopes for finding clues to this new physics.
So mesons are probes for this new physics. You mentioned two frontiers for finding it, energy and precision.
That's right. The energy frontier tries to make new heavy particles directly. Think ATLAS and CMS at the LHC smashing protons with huge energy, making new particles directly.
The precision frontier looks for indirect signs. Experiments like LHCb and Bell II make incredibly precise measurements of known processes, especially rare meson decays.
How does that find new physics?
Even if a new particle is too heavy to create directly, it can still participate in processes virtually popping in and out of existence briefly in quantum loops. This can slightly change decay rates or how particles fly out compared to the standard model's prediction. So you look for tiny deviations from what the standard model says should happen.
Exactly. Measuring a deviation, however small, can point to new particles or forces at energy scales potentially far beyond what the LHC can reach directly.
And LHCb and Bell II are complementary in this.
Very much so. Bell II, using the Super Kiki BE Pluck E collider, creates very clean pairs of B-mesons, D-mesons, and tau leptons. Low background noise, ideal for certain high-precision measurements and searching for potentially light, new, weakly interacting particles.
Clean environment. And LHCb.
LHCb, using the LHC's proton-proton collisions, benefits from the sheer number of heavy quarks produced. Although the environment is messier, they can study extremely rare decays in the full range of B hadrons, including baryons and rarer mesons. They've also excelled at finding those exotic hadrons.
So different strengths, covering different angles.
Precisely. Together, they're mapping the landscape of flavor physics. Searching for exotics, measuring CP violation, hunting for rare decays, it's all connected. Any confirmed deviation from the standard model in Meson behavior could be the crack that leads to a revolution in our understanding.
It's really quite a journey for the Meson, from a theoretical glue particle to this incredibly versatile tool.
It truly is. Its importance has just grown and evolved. It started as Yukawa's brilliant idea for nuclear cohesion, became a key part of the particle zoo organized by the quark model, served as a crucial laboratory for testing QCD. Think of the pion mass and chiral symmetry, or the hunt for glue balls, and now stands as a precision probe for the biggest mysteries remaining, like CP violation and the search for physics beyond the standard model. We've seen this amazing dualism, the nuclear glue and effective theories, the zoo organized by quarks, confirming charm and bottom, a laboratory for QCD, testing confinement, symmetry breaking, probing the gluon field via exotics, and a probe of new physics, using heavy mesons to search for tiny cracks in the standard model, especially regarding matter-antimatter asymmetry.
So what does this all mean for you listening in? It means these tiny, fleeting things are windows onto the universe's deepest workings. Hopefully, this deep dive gives you a solid footing. But the questions definitely don't end here. You have to wonder, what is the real structure of those tetraquarks? Are they compact or like molecules? Will we nail down a definitive glue ball discovery? That feels like a holy grail.
Huge questions remain.
And where are those extra sources of CP violation needed for our matter-filled universe hiding? Will B-meson or D-meson decays finally show that critical deviation from the standard model?
That's what thousands of physicists are working to find out.
And will the next generation of data from LHCb and Bell-Desecker reveal something completely unexpected in rare decays? It really feels like we're on the cusp of potential breakthroughs. The Meson predicted almost a century ago. It really is the gift that keeps on giving in physics. It's been central to so much, and it clearly remains right at the heart of our quest to understand the fundamental laws of nature.